Okay, so quick look at independence. How to determine if two things are independent. So, quick example. Again, the idea of independence is the event from one outcome doesn't influence the next outcome. So, let's say we're taking a job that requires us to fly from Atlanta to Houston every Monday. Website for this airline reports 85% of the flights are on time. So we want to look from week to week. What if the flights this week are going to affect next week? Essentially, the chance that a flight will be on time 2 weeks in a row. So does being on time this week have an impact on being on time next week? And I think that we all kind of have that intuition that no, it's not going to affect one to the other. So these would be an example of things that are independent. Uh, And then we look over here, another example, a survey of college students, 56% are on campus, 62% have a meal plan, and 42% are on campus and have a meal plan. So we're just going to walk around campus. And so our event here is the chance that a random person has not only a meal plan, but also is on campus. So when you think about independence, does being on campus have an impact on the meal plan? And again, intuition probably tells us if you're on campus, there's probably a good chance that that'll affect whether or not you do have a meal plan. So these two things are actually not independent. The issue for us is though we don't always want to trust our intuition. We want to figure out some way, is there a way to determine mathematically whether things are or are not independent? And yes, um, before we move forward, the test for independence for us is going to be based on conditional probability. Uh, there's two ways we can think about this. The probability of A given that B has occurred will be equal to the probability of A. In other words, right, if we think about this, this is the probability of A occurring given that B has occurred. We know that B has already occurred, but if you look at this, and excuse me if I didn't spell occurred right, I don't feel like changing it now. The probability of A occurring given that B occurred is the same thing as just A happening. In other words, A has no bearing. This can be the same as A happening. So in other words, B has had no impact on whether or not A happened. A happened regardless of B. Um, so another way we can rewrite that, though, you could also write it the other way. The probability of B given A is the same thing as the probability of B. The way that I always remember it is the event that comes first in my conditional is the one that's going to be by itself here. So you can see B given A is the same as B, or we go back to the first one, A given B is the same thing as A, right? So the first letter in the conditional is the same as the one that's isolated or all by itself on the other part of your equation. Let's put some numbers to it. 56% of American workers have a retirement plan, so we go retirement plan. They have it, so that will be 0.56. 68% have a health insurance plan, so there's a health plan, and there's that 68%. And 49% have both. So that will be have and have. So put that in that particular box. And we now have enough information to fill in the remainder of this chart. So remember, the total will always be 100%, which puts me at 44% of Americans don't have a retirement plan, and 32% don't have a health plan. Filling in the gaps here, this would be 7% of folks have the retirement plan but don't have a health plan. This would be 19% of people have a health plan but don't have retirement. And that leaves me with 25% that don't have either. So, real quick reminder about conditional probability. What's the probability someone has a health plan given that they have a retirement plan? So this goes back to what we discussed in class today. Recall the conditional probability. This would be health and retirement over the probability that someone has a retirement plan. So keep in mind your conditional probabilities from earlier today. So the health and retirement, in other words, both That's going to sit right there in that corner. That's the 0.49. And then the probability that you have a retirement plan. So that's going to be have a retirement plan, 0.56. So with that probability is 0.875. Take a step back and think about that. Most of the people that have the retirement plan, right? If you look at the folks that have the retirement plan, most of them do have a health plan as well. So there's a pretty great probability, if we know that they've already gotten the retirement plan, a big chunk of those folks already have the health plan as well. So it should be a pretty high probability, which is what we got here. In other words, not a lot of people with a retirement plan don't have health insurance. All right. So let's take a look at independence, right? There's a look back at what we did in class. Let's take the next step, independence. So are these independent? In other words, there's the probability of a health plan, given that you have a retirement plan, does that equal, and again, remember for independence, you take that first letter, and that's one by itself. So are those two things equal? Well, to save myself a little bit of work, we just figured out the probability of health given retirement on this previous page. So the probability of a health plan given that you would know you have a retirement plan was 0.875. So probability of a health plan given a retirement plan equals 0.875. The probability that someone just has a health plan, if we look back up here, here's health plan, here's has a health plan, that would be 0.68. And doesn't take much to realize these two things are not equal, which means that there's some kind of there's one of these is having an effect on the other. But these two things, because this is not equal, these two things are not independent. So apparently there is some kind of effect having a health plan and having a retirement plan. Intuition would tell you probably most people that have that retirement plan set up are probably going to be responsible enough also to go ahead and have health insurance. So intuition tells us there's probably a relationship there anyway. A lot of jobs with benefits as well, but that's getting beyond what we're really after here. Another example, police reports. This is an example we saw in class. 78% are given a breath test. And I'm just going to go ahead and do this, which means 22% are given neither, or not given a breath test, excuse me. 36% are given a blood test, which means that 64% of people are not given a blood test. 22% get both, so breath and blood. There's the 22%. Take a quick second here, fill in the rest of the chart. That means 56% goes there. This will be 14%, which is that 8% of the people get neither a breath nor a blood test when stopped on the suspicion of drunk driving. So, are blood test and breath test independent? In other words, the probability that we are given a blood test given that we've been administered the breath test, is that equal to, and again, take that first one there, is that equal to the probability that we're just given a blood test or the individual stopped? I guess I should stop saying us. We would never be pulled over on a suspicion. Better not, anyway. So, very quickly, so blood, given that you've had a breath test, so that would be a probability of a blood test and a breath test divided by the probability of breath test. So blood and breath, there's blood and breath is 22%, and the probability of just a breath test, right? In other words, right, most people, when we think about people getting pulled for drunk driving, the breath test is probably the one they're most likely given. 78% of the people are given that. Not many police officers administering blood tests on the side of the road. So that probability, blood and breath divided by breath is 0.28 approximately. And probability of blood test, that's very easily defined. Right there in the chart, 0.36. These two things are definitely not equal. which means, again, here's another example. These things are not independent. So chances are there's some kind of relationship between if you're given the breath test and if you're given the blood test. Um, I do want to take a quick second and make sure you don't mistake mutually exclusive. Obviously, there's overlap, right? Both tests. That's going back to mutually exclusive. So obviously, these things, there is an overlap, but that doesn't necessarily mean that things are independent. You want to make sure you go through the process right here, right? Make sure you use that conditional probability to test for independence. So another example here, one more example. Let's say in our standard deck of playing cards, right, the 52 cards in a deck, just for those of you that aren't card experts. Um, how about Jack and Heart? Obviously, there's an overlap. There's a Jack of Hearts. So here's another example where there's these things that do have an overlap. Let's see if these two, draw Jack, if you draw a Heart, are those independent of each other? So in order to do this, again, so the probability of Jack, given that you have a Heart, is equal to the probability you get a Jack. So the probability right here would be Jack and Heart. Probability of a Heart. So the probability you get the Jack and a Heart at the same time, how many cards out there are both a Jack and a Heart? Well, that's 1 out of the 52. And then the probability that you get a Heart, well, there are 13 of those, out of the 52, should be 1/13. And then the probability you get a Jack is 4 out of the 52, which will simplify to 1/13. Now all of a sudden we can see those two events are in fact equal, which means we have two events that are independent.